Hello, friends. Welcome to Science Talk. I am your host and resident oceanographer, Jim Massa. I want to share with you a couple of recent abstracts detailing some findings involving the North Atlantic and the Arctic. And I will leave the URLs to the two papers I'm going to feature in the comments section for those of you who want to do a deep dive. I'm just going to share with you the major findings of these papers and the implications and what they mean. So first, to start off, this is a paper that was published on 26th October of 2021. And the title of the paper is The Response of North Atlantic and Atlantic Meridional Overturning Circulation to Reduced and Enhanced Wind Stress Forcing. The authors are Lohman, Putrasayan, von Storch, this is Gutjahr, Jungklaus, and Hack. So, what's the overall finding that they found? And I'm reading from the abstract. Surface wind stress strongly influences Atlantic meridional overturning circulation, AMOC, variability on interannual timescales. On longer timescales, however, its role in AMOC variations is less clear. Here we show a nonlinear AMOC response to globally reduced and enhanced wind stress forcing based on sensitivity experiments with MPI ESM 1 and 2, basically some models that they use. Under reduced wind stress forcing, AMOC strength strongly decreases. In contrast, under enhanced wind stress forcing, the AMOC strength increases only in the first decades and then decreases, stabilizing at a value similar to the reference simulation. To reveal possible mechanisms underlying this response, we assess the response of the northern North Atlantic circulation and climate to the change wind stress forcing. Initially, the response is linear. Reduced wind stress forcing weakens the gyrocirculation and the associated heat and salt transport. We'll get to that. I'll return to that point later. So the associated heat and salt transport leading to larger winter sea ice extent and a shutdown of subpolar deep convection. In the Nordic seas, the fresher and lighter subsurface state leads to a decrease in the baroclinic pressure and the overflow strength. In oceanography, we often talk about baroclinic and barotrophic surfaces. It has to do oftentimes following isopycnal lines or parallel to isopycnal lines. If you guys are interested, I can do a video explaining baroclinic and barotropic. So leave a comment in the comments section. But for our purposes here, we need not be too concerned about that. Under enhanced wind stress forcing, initially the opposite is happening. However, eventually, subpolar surface density anomalies are determined by warmer temperature rather than increased salinity, leading to a decrease in surface density and a weakening of subpolar deep convection. The resulting AMOC weakening reduces the Atlantic inflow salinity, that means waters flowing from south to north, and subsequently the Nordic Sea's baroclinic pressure and overflow strength. The quasi-equilibrium response of the northern North Atlantic circulation and climate. Here we show a nonlinear response of AMOC to reduce and enhance wind stress forcing based on sensitivity experiments with the MPIM climate model. Under reduced wind stress forcing, AMOC strength strongly decreases. In contrast, under enhanced wind stress forcing, AMOC strength increases only initially, then decreases and stabilizes at a value similar to AMOC strength under unchanged wind stress forcing. The initial linear AMOC response to reduce, enhance wind stress forcing involves a shutdown, intensification of both subpolar deep water formation and export of deep water masses from the Nordic seas. The afterward different response under enhanced wind stress forcing is mainly caused by the fact that eventually subpolar surface density anomalies are determined by temperature decrease in density due to warming, rather than salinity anomalies, increase in density due to increased salinity, which leads to a decrease in surface density and a weakening of subpolar deep water formation. Okay, so there's a lot to unravel from that, if you will. So let's start with the role of wind. Okay, wind blows on the surface of the water. That it induces a forcing, and that forcing will be manifested itself in surface currents, and as I explained in my rotating systems video, you then create what's called an Ekman spiral. And the Ekman spiral is basically, how, as the wind pushes on the surface water, and then that surface water pushes on the underlying layer of water, and that layer of water pushes on the underlying layer of water underneath that, etc., etc. And each time it does that, the magnitude decreases, but there's always a little deflection of approximately 45 degrees to the right in the northern hemisphere, left in the southern hemisphere, such that you can then integrate over the entire column down to what's called Ekman depth, and you can then calculate a mass transport, because the water en masse has a net transport to the right, northern hemisphere, to the left, southern hemisphere. So stronger winds would imply stronger mixing, and then especially when you have the heat given off to the atmosphere, so that the water gets cool and saltier, and gets colder and saltier, it then starts sinking, and there's your start of the conveyor belt with the deep flow of the North Atlantic deep water back towards the equator and eventually towards Antarctica. So that's basically the role of the wind. And what they're saying is, not surprisingly, is that if the wind stress is reduced, it's going to reduce the interactions and possibly in the deep water formation. When it's increased, it will increase it at first, but then at some point it stabilizes. So what does that mean? We know that, in essence, the heat is given off so that water in the North Atlantic cools down, becomes denser, it's pretty salty, putting aside freshwater input. What they're basically saying is that the wind action helps with the deep water formation. Now, so that's the role of wind there. That, according to what these guys are saying and my interpretation of what they're saying. Now we take into account the freshwater lens that's happening. Well, if we have reduced wind, okay, the gyrocirculation is going to be weaker. Associated heat and salt transport is going to be reduced. In other words, that is a way of saying the Gulf Stream is slowing down. Gulf Stream is slowing down. It's not going to bring the heat and the salt. And also, that then, by continuity of volume considerations, you then replacing that with colder, fresher water. And that will then, because now you have this cold or fresher water on the surface, you're basically creating stratified water that's going to impact any of the deep convection, what they call a subpolar deep convection. So that would be in the air. Basically, the Jin-C region is where they're referring to here. There are some other papers, a little side note here, there's some other papers that are showing that the halocline is being affected in the Arctic Ocean, and that is impacting the vertical mixing ventilation that's going on in the Arctic Ocean, and what it does if it gets down to the basin and so on. And that kind of builds on the work of Rebecca Woodgate and her team, where she's documenting seasonality changes in the halocline, in the strength of it, how stratified it is, and where it occurs in the water column. Some cases getting shallower, other cases going a little deeper. So it's a very dynamical system that's going on here. So if you have this, fresher, less dense, situation, it's going to obviously impact deep water formation, slow it down. And what they're saying here, according to their findings and their simulations, is that temperature appears to be more the driver than salinity. That's very interesting, because that is, well, we're kind of blunt about it. It's kind of counter to most of what I've learned and most of what my own research found, which is, now granted, wasn't in the Jin-C, was in the Arctic, but usually typically temperature is the main driver of density in tropical waters. Salinity is the main driver of density in polar waters. So this is an interesting result here. And, so I'm sharing with you what they're finding. I'll be honest, when I went through the paper, I wasn't convinced of their assigning the importance to temperature being more influential than salinity anomalies. But, this is science. To me, what the important aspect of this is what we already know. We have freshwater lens that's slowing down AMOC, but this in turn is affected by wind stress. So there is a coupling of atmospheric processes with what's happening in the surface waters of, in this case, of the North Atlantic. So it's not just merely, give off its heat, get cold and dense and sink, or throw a freshwater lens on the surface and it won't sink. There's a role of wind forcing into whether or not this takes place and to what extent. That's basically what I'm taking as the overall information out of all of this, and that I'm sharing with you. So there's that. And as I said, I will leave the URL for those who are interested in looking at this paper in detail. The next quick little abstract I wish to share with you is a paper that appeared in Geophysical Research Letters. It was published 16 December 2021, and the title of the paper is Emerging Trends in Arctic Solar Absorption, and the authors are Sled and Lecuyer. And this is a very wonky paper, a lot of details and stuff like that. I thought it would be important to just simply bring to you, the main take-home message, the main information, what is important to given our current climate situation. And a lot of this may appear to be, well, duh, but like anything else in science, it's one thing to speculate, hypothesize. It's another thing to collect the data that verifies or refutes. Okay, people have been suspecting that the Arctic is warming. Well, this study provides the data that shows by how much that the Arctic is indeed warming. Oh, from the abstract. Recent satellite observations confirm that the Arctic is absorbing more solar radiation now than at the start of this century. So that's just in 20 years, what the base is saying. In response to declining Arctic sea ice and snow covers. Makes sense. No ice, no ice, less ice, no snow, less snow. You reduce the albedo, which means less reflectance of energy back into the atmosphere, more absorption. And we can measure now usually watts per square meter, right? I did an overall AGGI video showing how overall for the planet, compared to like 1992 baseline levels, per square meter, the planet's absorbing 47% more sun energy, which is a bit. Oh, trends in the solar radiation input to Arctic Ocean and land surfaces now each exceed interannual variability at the 95% confidence level. Now, that's significant. Although all sky trends have taken 20 to 40% longer to emerge compared to clear sky conditions. Well, that makes sense. If you got clear skies, there's nothing to impede the incoming solar radiation. So, if you have dark surfaces, land or open water, more sunlight energy gets absorbed. You got clouds in the way, you're going to have reflectance off the top of the cloud. The sunlight attenuates going through the clouds, depending, of course, on the type of clouds, where it's found at the altitude, the thickness of the cloud layers, and so forth. Partly cloudy skies, totally cloudy skies, and so on. So all these will impact, or interfere with the solar radiation reaching the surface. So clouds reduce the mean solar absorption and secular trends over both land and ocean, but the effect of clouds on natural variability depends on the underlying surface. While clouds increase the time needed to unambiguously identify trends in nearly all Arctic regions, their masking effects are strongest over oceans. Clouds have extended the time to emergence of already observed clear sky trends beyond the existing 21 years. Clouds and Earth's radiant energy system record in half of 8 Arctic seas, supporting the need for continued satellite-based radiative flux observations over the Arctic. So a little look at the plain language summary. The Arctic has been rapidly changing in response to rising greenhouse gases, including dramatic sea ice loss. Sea ice is bright and reflects most sunlight that hits it, albedo, right? So when it melts, more sunlight is absorbed at the surface, leading to more surface melting or warming, positive feedback loop. However, when viewed from satellites in space, it can be difficult to distinguish between bright clouds and the bright surface. Because clouds also reflect a large amount of incoming sunlight, they reduce the amount of sunlight that reaches the surface. Without clouds, far more sunlight would have been absorbed into the Arctic over the last 2 decades. The presence of clouds has also made it more difficult to observe how the amount of sunlight being absorbed is changing. Nevertheless, the Arctic has been evolving so quickly that even with the masking effect of clouds, we can measure trends in absorbed sunlight using 20 years of satellite observations, relatively short amount of time compared to most other climate changes. Now, there's an interesting thing there, and a lot of this depends on the types of satellites that are used, what the sensitivity is calibrated for, what wavelengths they're looking at, aperture, all that kind of stuff there. And you have to look at the reflectance, and usually, depending on the time it takes for the beams to reach the surface, to reach whatever surface it's reflecting off of, and return back to the satellite, you can get an idea whether you're hitting the cloud or the ice. But most of the time, when we use when we present sea ice extent data, it's relying on satellite observations. Very rarely do you actually get out there and start mapping it physically, i.e., some sort of research vessel, research equipment, that people actually operate versus, excuse me, versus satellites, going overhead. So oftentimes, and this comes especially with the sea ice, sometimes greasy, fragile ice may be recorded as sea ice. Now, greasy and fragile ice, I basically refer to as slush, not really ice. It's sea ice in the process of being formed, but you can't stand on it. And to me, ice is something you can stand on, and you're not exactly going to be standing on slush. So it makes me wonder what kind of biases have been introduced into the satellite data. It would be interesting to see if someone can review the data, maybe look at it a little more critically, maybe make some adjustments to the measurements and so forth. So, how does that relate to cloud covers? Well, the satellites could, sometimes they mistake clouds for ice and ice for clouds, especially if you have clouds that are low in altitude. Again, possible further biases. But the point here is that they are showing increased measurements of solar radiation reaching the surface. It takes longer to go through clouds, not so long to go through the clear skies. And that makes sense. But in this paper, again, I'll leave the URL. In this paper, they present the data that shows this and verifies it, and shows that, more importantly, that the amount of increased solar radiation reaching the surface is significantly different. Now, this is a clear trend of ever increasing solar input. This is, the reduced albedo, etc. The major reason why the Arctic is now at least 3 times as much warming faster than the rest of the planet. There's been a recent paper stating that the Arctic is really warming 4 times faster than the rest of the planet. What was the difference here? Well, in the paper, in the current paradigm of 3 times faster, the researchers looked at the heat budget, the heat energy input from 60 degrees north to the pole. Papers saying 4 times faster, they're looking at it from the Arctic Circle to the pole. Now, the Arctic Circle is approximately about 66 degrees north latitude and some minutes to it. So basically, they reduced it from 60 to 90 to 66 to 90 as far as what latitudes to consider. And when you consider that each degree of latitude is approximately 60 miles, 100 kilometers, we're talking, what's that? The 360 miles, 600 kilometers. So that is a large expanse of land to no longer consider. Do with that as you wish, but I find that rather interesting. That it's almost like a fine tuning. That let's go from the Arctic Circle to the pole. But of course, the Arctic Circle is not fixed. It's not a fixed latitude. It's always changing. It changes because the Earth's axis, the tilt of it, is always changing. So the more it tips over, the further south the Arctic Circle will be, and the more to vertical that it goes, the further north the Arctic Circle will be. So that's almost changing a parameter, which will thereby always be changing the results. So I'm a little cautious about going with that. 60 degrees latitude, yeah, we can measure that. We know it's there. So that to me might be a more consistent approach to if you want to measure, any such heat/warming trends. Be that as it may, here, this presents data showing indeed how much the Arctic and polar region is warming. So, a couple of quick headlines, and thank you for your time. Hello, folks. This is Jim here with Science Talk, asking you to please subscribe to my channel and to inform others of my channel and of the work that I do. Please share to social media platforms that you use. Also, as a reminder, don't forget to click the bell so that you know when I load up more videos. Finally, I ask that you support the work that I do by becoming a patron at patreon.com. Details in the description box below. Thank you for your support.